Okay, so in a previous video, I showed an interesting technique on how to evaluate square roots without needing to use a calculator. And in that video, I used a cool trick or a shortcut for evaluating continued fractions. So let's start a new theorem. Let the partial fractions of a0 plus 1 over a1 plus 1 over a2 plus 1 over a3 and so on be denoted p0 over q0, p1 over q1, p2 over q2 and so on, where we have, for example, a0 is equal to p0 on q0. And we also have that a1, a0 plus 1 over a1, equals p1 over q1, and then a0 plus 1 over a1 plus 1 over a2 is equal to p2 over q2, and so on and so forth. What we can do is we can show, and the theorem that I'm about to say, we can show that we can evaluate these as Pn over Qn is equal to An times Pn minus 1 plus Pn minus 2 over An times Qn minus 1 plus Qn minus 2, wherever n is greater than or equal to 2. Because obviously we need to find P0 and P1 the old-fashioned way, and that's easy enough to do. It'll come out nicely in this proof. So when we have values greater than 2, then we can just evaluate the next term in this sequence with this little shortcut. And what I'm going to do, that's not the end of the proof there, that's the end of the theorem. What I'm going to do is show why this is true. So let's start proving it. So note that P0 over Q0 equals A0 over 1. Therefore, we can say that P0 is A0 and Q0 equals 1. Right? That's the simplest form of this fraction. Straightforward. P1 over Q1 is equal to A0 plus 1 over A1, which is equal to A0 A1 plus 1 over A1. So this gives us P1 over Q1. This also is straightforward to see. And finally, lastly, P2 over Q2 is equal to A0 plus 1 over A1 plus 1 over A2. And what I'm going to do here to do a quick shortcut is I'm going to treat all of this the same way I treated A1 over here. So when I have x plus 1 over y, we can see quite straightforward. It's going to be x times y plus 1 over y. So let's just do that. It's going to be x times y plus 1 over all of y. A1 plus 1 over A2. And then we can clean up the stuff on the inside as well. We can apply the same rule. Well, and that's going to be A0 outside of x times y, A1, A2 plus 1 over y, which is A2. And then we just go plus 1 over, same thing here, A1, A2 plus 1 over A2. I'm going to bring the A2 that's down the bottom up the top here, and that's going to become a0, a1, a2 plus 1 plus a2 over a1, a2 plus 1. And we can see that this is going to take the same form that's conjectured up here in our theorem, because here we have, well, that's equal to a2 all being multiplied by a0, a1, because that's a2 times a0 times a1 plus 1, because that's a2 times 1. And then just plus a0 all over a2 times a1 plus 1. But this a0, a1 plus 1 is my p1 that I had up here. p1 is equal to that. q1 is equal to a1. So this is actually a2 times p1 plus a0 was my p0. So a1, a2 p1 plus p0 over a2 q1 plus, and then 1 was also q0 plus q0. So therefore, the theorem holds for n equals 2. And we can prove it by induction. So now let our inductive step be, well, suppose, oops, sorry for bumping the camera, that happens a lot, I need to get a new setup. Suppose that pk over qk is equal to ak times pk minus 1 plus pk minus 2 over ak times qk minus 1 plus qk minus 2 for some k bigger than or equal to 2. So suppose that's the case. Well, that's our inductive hypothesis. Then pk plus 1 over qk plus 1 is equal to a0 plus 1 over a1 plus 1 over a2 plus dot 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 1 over pk, 1 over ak plus 1 over ak plus 1. That's how we define our partial fractions. Well, I know what all of this is. So actually, if I want, what I can do is I can say, well, actually, this is equal to this partial fraction. Where now, instead of using the previous value for ak, we just make it slightly different. We just make it the stuff in these parentheses, which it's still going to have the same form as our inductive hypothesis. It's still going to match this because the hypothesis cares about the number of terms in the sequence. We just gave it the general coefficient of ak at the front, or the general quotient of ak. So when I add all of this up, well, that's going to be this. This is my new coefficient that comes out the front of the top and the bottom. So it's all of that times pk minus 1 plus pk minus 2 over, and then the same thing, times qk minus 1 plus qk minus 2. So that's by my inductive hypothesis. By the inductive hypothesis. Okay, well, let's clean this up a bit. That's going to be ak plus 1 over ak plus 1 times pk minus 1 plus pk minus 2, and then same thing on the bottom. ak plus 1 over ak. And you can probably see where this is going because we basically did the same thing just before, except instead of using AK and AK plus 1, we used A0 and A1, I believe. So we've pretty much done the same thing, we're just doing it more generally for any term AK, not just A2. Then I can multiply out by AK plus 1. And that becomes AK plus 1 times PK minus 1 plus AK plus 1 times PK minus 2 all over, same thing on the bottom, AK plus 1 QK minus 1 plus AK plus 1 QK minus 2. So I've just multiplied both the numerator and denominator by AK plus 1. Then from here we can take out a common factor of AK plus 1 from the top and the bottom, so that common factor of AK plus 1 is attached to AK PK minus 1 plus PK minus 2, and then plus PK minus 1. And then I do the same thing on the bottom. So I take out the factor of AK plus 1, and that's attached to AK Q K minus 1 plus Q K minus 2 plus Q K minus 1 from here. And from here, we're almost done, because all of this is PK from my inductive hypothesis. So if we go back up here to the inductive hypothesis, AK PK minus 1 plus PK minus 2 is all equal to PK. So all of this is equal to PK times PK, and then plus PK minus 1 over, and then same thing on the bottom, by my inductive hypothesis, that's going to be QK plus QK minus 1 by inductive hypothesis, which is just equal to AK plus 1 times PK plus 1 minus 1 plus QK plus 1 minus 2. Sorry, P. That should be a P on top. And then same thing on the bottom. So now all I'm doing here is I'm just making it very explicit that this follows the same general form that was given in the original theorem. Oh, sorry, I didn't mean to bump that. That was given in the original theorem. Therefore, by mathematical induction, because PK over QK following the rule implies PK plus 1 over QK plus 1 also follows the rule. For all k greater than or equal to 2, then Pn over P over Qn is equal to An multiplied by what? Multiplied by Pn minus 1 plus Pn minus 2 over An times Qn minus 1 plus Qn minus 2 for all n greater than or equal to 2. And we're done. We're done because we just showed it. We just showed by mathematical induction that that's going to be the case. So that's why I could use that rule to evaluate those partial fractions. And we also see here that this is, I guess, a bit more general than what I was just insinuating over in that previous video, because this works for any recurring partial fraction. It will always follow this rule. Doesn't matter if it's a repeating fraction, it doesn't have to repeat. It can follow any any sort of pattern, A1, A2, A3, can be any numbers whatsoever. They don't even necessarily have to be integers. It wouldn't make sense to write out a partial fraction without integers. That's kind of that's their thing. I guess you could use rationals. Or irrational numbers if you really wanted to. But yeah, it's always going to follow this rule. And you can always use that to evaluate the nth term. There are also further methods that you can do that can even more quickly evaluate several steps ahead. So there's a second theorem which I might go over in a future video, which basically lets me, if I know what Pn and Qn are, then I can find P2n and Q2n. So I can essentially get double the steps ahead. And in that case, for that future proof, I believe it only works when it is a recurring fraction. You might want to play around with it and see if you can devise the rule on your own. But then if I can go from Pn over Qn to P2n over Q2n, then I can use the 2n to go up to 4n. Then I can use the 4n to go up to 8n and the 8n to go up to 16n. So I can, in theory, use the other theorem to more quickly evaluate things. Yeah, so thank you for watching. Hope that you followed that along. Hope that the camera wasn't too shaky. I do need to get a better filming setup. Yeah, see ya.